So we're now going to talk about how to use Java Lambda expressions correctly and efficiently. And this will build on our earlier discussion of what a Lambda expression is and then show some interesting ways they can be applied. So one thing to keep in mind about Lambda expressions, you can't use them to modify variables that are defined outside of their scope. And if you try to do that, for example, if we write this little piece of code where we've got a variable called answer that's defined outside of the scope of the Lambda expression, and we try to set it inside the scope of the Lambda expression, you're going to get an error that'll say something like variable used in Lambda expression should be final or effectively final. And I'll talk more about that in a second. And we'll look at this code in more context when we look at the case study here shortly. Now, that's one thing. You have to be careful. I'll show you some ways to work around this issue in just a moment, but just be aware that you can't modify them outside of their scope. Likewise, if the body of the Lambda is a block of statements, or if the Lambda has no value and is not a single void method invocation, then you have to surround the Lambda with curly braces, as I'm showing here. So you can see that in this case, we're going to surround it with curly braces, even though, of course, it's still not going to compile because we haven't solved the problem about answer being defined outside the scope. But you need to put the curly braces around that particular block. So you can only access final or effectively final variables within the context of a Lambda expression. So what is an effectively final variable? An effectively final variable is a variable that's not actually defined as final, but whose value never changes after it's initialized. So, of course, a final variable is something you mark as final. You can think of final in Java as being something akin to a const in a language like C or C++. So you can have something that's effectively final, as we have here. And since we're only accessing it, but not trying to change it after it's initialized, it's effectively final. And you can read more about effectively final in this link at the bottom of the slide. So here you can see it works perfectly fine because we're setting it outside the scope, but we're only reading it. So as long as it's read-only, then everything's OK. Here's one workaround for this restriction, because sometimes it's actually a little annoying not to be able to assign something within the scope of Lambda expression and then use the value somewhere else. So one way to do this, which is a little bit of a hack, is to create a one-element array and then assign and use item 0 in that array. So you can see we can access array sub 0, set that to 42. We can then read the value of the array sub 0, and so on and so forth. And then you can do something with the updated array element after the Lambda expression is done. The problem with this is that you have all the other drawbacks that we come to know and love with so-called mutable shared state. And we'll talk a lot about that throughout the course. That's a big challenge in concurrent programs, is avoiding race conditions and other evils that come with using mutable shared state. Another way to solve this problem, which is more elegant, is to use an atomic object, like an atomic integer. So here we assign answer to be an atomic integer, which is initialized to 0. Then we can set its value within the scope of the Lambda expression. We can read its value using get. When we're all done, we can get the answer back that we've set, and so on and so forth. And all of this will be done atomically and will be done in a way that preserves the semantics that Lambda expressions have, because we're not changing answer, we're changing a value of answer, because value is now a reference type. The only downside is that there's some minor synchronization overhead. Very, very, very little, by the way. But just be aware of that. This solution, of course, is thread safe because an atomic integer is thread safe, and we'll look at that later in the course. But there is some minor overhead. Lambda expressions are most effective when they're stateless and have no shared mutable state. And this is particularly important when you use them with Java parallel streams, where you need to be able to ensure that the parameters that are passed to the method don't have any side effects. So here's a simple example. This is a capitalized method that takes a string parameter. It's stateless. Its return value is the same for the same arguments. There's no reading of shared mutable state. Its evaluation has no side effects. There's no writing to shared mutable state. So pure functions are very useful when we start trying to deal with concurrent programs. And you'll see lots of examples of those as we go through this material. So that's the end of the overview of using Java Lambda expressions correctly and efficiently.